Hello everyone, myself MANISHA MISHRA. I am an assistant professor in mathematics, applied science department at St. Andrews Institute of Technology and Management, Gurgaon. Today I will discuss the topic of complex analysis here. Now let's begin it. So first topic is your complex analysis topic is your complex variable. So what is complex numbers? Let x and y be two real numbers. Then z is equal to x plus iota y is a complex variable. So this part x is your real part and this part y is your an imaginary part. Why it is real and why it is imaginary? Because iota is here. So which that part is including iota. So that part is your imaginary part and that part is your real part. So where iota square is equal to -1, this is the value of iota. Iota is equal to square root of -1. Then z is equal to x plus iota y is called complex number, and this form is called Cartesian form. XY form always a Cartesian form, and r theta form is your polar form. So now next one is your put Cartesian form, to convert Cartesian form into polar form, we need to find x and y. So put x is equal to r cos theta and y is equal to r sin theta here. So z is equal to r cos theta plus I r sin theta. And these values x and y are coming from this figure. So this figure is your this one is your x-axis is your vertical horizontal axis, and y-axis is your vertical axis, and this point P r theta. So just find the value of cos theta here. So cos theta is your x upon r. R means the hypotenuse. A square root of x square plus y square. So r is equal to x is equal to r cos theta, y is equal to r sin theta. Just simple put the value of x and y here. So z is equal to r cos theta plus I r sin theta. Now r is common, then taking outside, and cos theta plus I sin theta is called polar form. Now we know that De Moivre's theorem. And what is De Moivre theorem? De Moivre theorem is cos theta plus I sin theta is equal to e to the power I theta. So we can write here cos theta plus I sin theta as e to the power I theta. So this is your new form. Z is equal to r e to the power I theta form. That is called exponential form. That means we have three form of complex variable. First one, z is equal to x plus iota y, that is called Cartesian form. Second one is your z is equal to r cos theta plus I sin theta, that is called your polar form. And next one is your z is equal to r e to the power I third, that is your exponential form. That means there are three form of Cartesian form. Now next one is your function of complex variable. So what is the function of complex variable? Let fz be a function of complex variable z and is denoted by w. Simply z is a function of x and y and w is a function of z, and w is equal to u plus iota v. Z is another plane, w is another plane. So z in z plane coordinates are x and y, in w plane coordinates are u and v. So u is your horizontal axis, v is your vertical axis, and u and v also are the real and imaginary part of the function fz respectively. And now next, differentiation. Differentiation means, as we know the continuity definition, continuous function definition, same as it is. What is the differentiation definition? So let fz be a single valued function of the variable z. Then f dash z, differentiation means f dash z derivative with respect to z is equal to limit z tends to z0 f of z plus z0 minus f of z0 upon z. This is your form. This is your formula. This is differentiation formula. Or we can write it as f dash z is equal to limit delta z tends to 0 f of z plus delta z minus f of z upon delta z. That means that z0 is replaced by delta z here. Provided that the limit exists and is independent of the path along delta z, which delta z tends to 0. Provided that the limit exists, that means if when we apply delta z tends to 0, then we will get this function free from of z, so is independent of the path along which delta z tends to 0. This is the meaning of this line. That means when we will apply the limit delta z tends to 0 or whatever which is given, then you will get this function is free from z. Now there is an example here. Consider the function fz, this one, then find del f upon del z is equal to f del z. So we have our function fz, and we know that w is equal to fz is equal to u plus iota v. So we can compare on both sides. So u is equal to this one and v is equal to this one. Now we need to find del f upon del z is equal to f del z. That means we need to find f of z plus delta z minus f of z upon delta z. So f of z is given here. So find f of the z plus delta z. So f of delta plus z plus delta z is equal to 4x plus delta x plus y plus delta y minus x plus delta x plus 4i y plus delta y. That means x is replaced by x plus delta x and y is replacing by y plus delta y. So f of z plus delta z minus f of z. So just write the value of here, and after solve cancellation the terms of these, then you will get remaining value this one. So this one is your f of z plus delta z minus f of z value. Now dividing by delta z, so you will get this one. So this value is your f dash z value. Del f upon del z is equal to this one. Now next example is here. If fz is equal to x cube y minus iota x upon x to the power 6 plus y square, z does not equal to 0. At z does not equal to 0, you are getting this function value, and at z is equal to 0, you are getting 0. So discuss del f upon del z at z is equal to 0. That means we need to find at z is equal to 0 what is the function the derivative value will be here. So if z tends to 0 along the vector y is equal to mx, limit z tends to 0 fz minus f0 upon z is equal to limit z tends to 0 f of z value is here minus f of 0 value is here. F of 0 value means f of z at 0. So this value is 0. So put right here 0 upon z. This one z upon. So x plus iota y. Now limit z tends to 0 minus iota x cube y x plus iota y upon this value. Now first thing we are check the along the vector y is equal to mx. Uh, if z tends to 0 along the vector y is equal to mx, we have two or three vectors. This one is your straight line passing through from origin, and we have another curve y is equal to x square or y is equal to x cube type. So we will check for all the vector all the along the all along the vectors. So now put y is equal to mx here, then you will get this value. If z tends to 0, that means x plus iota y also be tends to 0. If x plus iota y tends to 0, that means x tends to 0 and y tends to 0. So this function is only in x form. So x tends to 0. So just put the value of x here, then you will get a value 0. That means at z tends to 0, you are getting 0 here. That means one part is clear to us. But along the new vector, new curve y is equal to x cube, if along this curve if we will get 0 here, then we can say this function is differentiable at z is equal to 0. But if the value is different, then we can say, when we cannot say that for this function is differentiable or not. So just first check along the curve y is equal to x cube. So put y is equal to x cube here. So you will get this value, and when you will apply the limit here, so you will get minus iota upon 2. So minus iota upon 2 is different from 0. So this value and this value does not equal to 0, then we can say this function is not differentiable at z is equal to 0. In different paths we get different values of del f upon del z or df upon dz. It means 0 and minus iota by 2. Hence, the given function is not differentiable at z is equal to 0. If value are same, then we can say this function is differentiable. But both values are different, so it is not differentiable. Now, next topic is your analytic function. Very important topic, analytic. So, a function fz is said to be analytic at a point z0 if f is differentiable not only at z0 but at every point of some neighborhood of z0. So, what is this mean? What is the meaning of this line? F is differentiable, that means limit will be exist but not only at z0. That means not only a single point z0. If there are another points z1, z2, z3 and so on, that means at all these points where function should be differentiable, then we can say the whole function fz is analytic at that point. So this is the meaning of this line. A function fz is analytic in a domain if it is analytic at every point of the domain. So this is your another way to represent analytic function. The point at which the function is not differentiable is called singular point of the function. Analytic function is also known as holomorphic, regular or monogenic. We can also say analytic function as holomorphic function, regular function or monogenic function. Now, next topic is your the necessary condition for fz to be analytic. Theorem. The necessary condition for a function fz is equal to u plus iota v to be analytic means, what is the necessary condition to the fz for the fz to be analytic at all points in a region R? Del u by del x is equal to del v upon del y. Del u upon del y is equal to minus del v upon del x, and provided these partial derivative must be exist. So what are these equation? These equation are called Cauchy-Riemann equation. Next one, Cauchy-Riemann equation, that means CR equation. So let W is equal to Fz is equal to U plus iota v be an analytic function. So this equation first and this equation second are known as Cauchy-Riemann equation or CR equations. If CR equation is satisfied, then function fz is your analytic function. That means these derivatives must be exist, and this condition and this condition, if both are satisfied, then we can say your function fz, this one, is an analytic function. There is a note here. Fz is equal to, we know that u plus iota v. So f dash z, that means derivative form your del u by del x plus iota del v upon del x, and or f dash z is equal to del v upon del y minus iota del u upon del y. So this value del u upon del x we can write del v upon del y, and del u upon del y, del v upon del x we can write minus del u upon del y. So this is your derivative form of your fz. Remark: if a function is analytic in a domain D, then UV satisfied CR conditions. That means if function fz is analytic, so U and V means real part, imaginary part of your function fz satisfied this CR equation. That means these derivative must be exist here. This derivative, these derivative will be exist. Now, second remark, CRic condition are necessary but not sufficient for analytic function. It is necessary condition but not sufficient. CRic condition are sufficient if the partial derivative are continuous. That means the partial derivative means del u by del x, del v upon del y, del u upon del y, and del v upon del x. These partial derivatives, if continuous, then CR equation will be a sufficient condition. Now there is an example here how we will find the analytic function by using CR equation. So show that the function e to the power x cos y plus I sin y is an analytic function. So, and also find its derivative. So first one, we have our function fz is equal to this one, and fz is your u plus iota v. So u plus iota v is equal to this one. So come on comparing both sides, then we will get u is equal to real part and v is your imaginary part. So we need to find CR equation, and CR equation is del u upon del x, del u upon del y, del v upon del x, and del v upon del y. These are partial derivatives, so just we need to find all these partial derivatives. So del u by del x, that means u is differentiating partially with respect to x. So another variable is y here, and in partial differentiation, another variable always treats like a constant. That means cos y will be your constant, and differentiating e to the power x with respect to x, same as it is. Now del u upon del y, that means e to the power x will be your constant, and cos y differentiation minus sin y. Del v upon del x, that means e to the power x differentiation, same as it is, and del v upon del y is equal to e to the power x cos y. So we have all our four derivatives. Now check the CR equation satisfied or not. So we know that this one and this one are CR equation. if this condition is satisfied. So left hand side is equal to right hand side here, and also here left hand side is equal to right hand side. That means CR equation are satisfied and the partial derivatives are continuous. So hence we can say our given function, this one is analytic. Now second is one your find derivative. So fz is equal to this one, and we know that the derivative form is, or f dash z is equal to del u upon del x plus I del v upon del x. So just we have our values del u upon del x and del v upon del x value. So just put here a value of del u upon del x this one and del v upon del x this one. So e to the power x common, so taking outside cos y plus I sin y, and y again De Moivre theorem, e to the power I theta is equal to cos theta plus I sin theta. So we can write here cos y plus I sin y as e to the power iy. So base are equal, so power can be added. So e to the power x plus iota y, and we know this value is z. So f dash z is equal to e to the power z. This is your derivative answer, and this one here the CR equation are satisfied and partial derivative also existing. Now next one is your above equation are in Cartesian form, because xy form is your Cartesian form. Now another equation, Cauchy-Riemann equation in polar form. So what is polar form? That means r theta form. So let w is equal to fz is equal to u plus iota v be a function. We know already this value. Now p r theta is a polar coordinate. So how we will change our Cartesian form into polar form? So first one, what is polar form? What is Cauchy-Riemann equation in polar form? So del u by del r is equal to 1 upon r del v upon del theta. Del u upon del theta is equal to minus r del v upon del r. This is our polar form, Cauchy equation in polar form. So how we are getting this equation from our Cauchy-Riemann equation in Cartesian form? So we know already this equation. We know that x is equal to r cos theta, y is equal to r sin theta, and u is a function of x and y. So z is equal to x plus iota y, we know that function. So put here r cos theta plus I r sin theta, and z is equal to r cos theta plus I sin theta, and z is equal to r e to the power I theta by De Moivre theorem. So this is your another form, exponential form. W is equal to fz is equal to u plus iota v. So u plus iota v, we can write here w is equal to f r e to the power I theta. In place of z, we can write here r e to the power I theta. This is your equation first. Now differentiate first partially with respect to r. So if we differentiate this equation with respect to r, then del u upon del r plus I del v upon del r is equal to function differentiation always dash here. So f dash r e to the power I theta into r e to the power I theta differentiation. So r is differentiating, so r differentiation is 1 and e to the power I theta as it is. This is your equation second. Now again differentiating first with respect to theta. So del u by del theta plus I del v upon del theta is equal to f dash r e to the power I theta into r e to the power I theta, and I theta is differentiating, so theta differentiation is 1 and I will be here. This is our equation third. Now substituting the value of this one from 2 in third, that means this is your equation second, and we can write this one in place of, we can write the value of this one in place of this one, f dash r e to the power I theta. So just put the value of this one here. So you will get del u upon del theta plus I del v upon del theta is equal to r del u upon del r plus I del v upon del r. Iota is again outside here. So just multiplying IR inside the bracket, then you will get this line, and equating real and imaginary part. So just when we will comparing when, on both side, then we will get del u by del theta is equal to minus r del v upon del r, and del u upon del r is equal to 1 upon r del v upon del theta. So this is your Cauchy-Riemann equation in polar form, and this is the proof of the equation where we will get all these formula, all these equation first and second. So this is your Cauchy-Riemann equation in polar form. So in next video I will discuss the topic of harmonic equation. So thank you.